Hello friends, good afternoon and welcome to EduSite live lectures. Dear friends, today in computer sciences, in network and graphs, we will be talking about fundamentals of graphs. To discuss this topic, we have with us our subject expert, Dr. Aditya Sinha. Dr. Aditya Sinha is Assistant Professor in Department of Computer Sciences in a prominent university in NCR of Delhi. Without further ado, I would like to welcome ma'am to our studios and request her to start the lecture. Welcome.
Thank you. Welcome viewers. In the last lecture on networks and graphs, we were studying about some introductory concepts on graph theory, right? So in this lecture, we'll take that more further and we'll study more fundamental and basic concepts on graphs. So let's start. So in this lecture, mainly we are going to cover the basic concepts that will include the graph, some more terminologies and certain metrics that will involve geodesic, the shortest path, how to calculate number of shortest paths that exist in a graph, and the average path length, the diameters in the graph, and this way there are more metrics that we have, and then we'll continue to simplifying how the network complexities are getting simplified using these metrics and the concepts, the basic ones and the little complicated ones. And then certainly we will talk about which nodes in the graph, any real-time network that is modeled in form of a graph, if it is given to us, then which nodes are more important to us, like in terms of the nodes that are having very highly compact neighborhood, or the nodes that are easy to reach in a certain amount of time, or some given constraints, or it can be some local patterns, etc. So we'll see all these things shortly. Starting with the basic concepts, we were talking about the components in the graph, right? So just to continue from there, the connected graph. If we are taking the undirected case of graph, in which the direction, the directivity, the flow of information or say packets, etc., it doesn't matter, that is the undirected case. So in undirected graph, what happens, at least one path is going to exist between any pair of nodes. This is the important constraint, and for connectivity it is also very important that it has to be a reachability parameter in it. If we are on any node, the node we know that it can be places, or it can be some station for wireless routing of packets or wired transmission, etc. So be on any node. If a person or a message or a transmission, a communication has to take place on any node, it should be able to reach to any other node in the network. Okay, and what else? It should be, in short, in brief, if we are talking about the single connected component. We know what is a component. So here, whenever a graph is having a single connected component, it means that it is a connected graph. Okay. And if we are taking the directed case into consideration, in it what happens, let's see in the diagram, that in this there has to be a reachability in addition to connectivity, because connectivity always doesn't mean that there is a bidirectional connection. Say if we are having a unidirectional connection, so that is the directivity is important in some of the cases. So here what happens, there has to be directivity in reachability, right? So in the diagram we can see that as a flow of arrows we can see here, over here, that if a person or a station is operating at some state A, then is there any possibility to go to state G? Yes, we can obviously check it out, A to B, B to E, and then E to G, right? Again, if there is a loop formation, E to G, G to F, and again F to E, and again we are reaching back to G, right? So this is the direction, and another figure, we can see that we have a graph with two different components. So this is certainly not a connected graph. Now what else? These are all connected graphs that we were discussing about. Now what is a strongly connected graph? Strongly connected means that every pair of node, if they are connected to each other by single hop, by a single link, then such graphs are called strongly connected graph. As in the figure, we can see that a node with a graph with three nodes A, B, C, they are all connected to each other, all are peers to each other. So since there are a total number of nodes 3, we can see that the edges here are also 3. Okay. If we are going to calculate two important parameters, rank and nullity, we can see over here that since it's a connected graph that we are talking about, so components will be obviously equal to 1. It cannot be more than equal to 1. So R equal to n minus k is the formula, where R is the rank, n is the total number of nodes, and k is the number of components. So in case of connected graph, it's needless to say that k will always be equal to 1. Okay, so if it's equal to 1, we can find out the rank of strongly connected graph. As in the first figure, you can see that it comes out to be 2. Nullity, which is also known as Betty's number, it is calculated with the formula mu is equal to E minus n plus k. N and k we know, E is the number of edges. So if we are applying those formula on the first figure, we find that nullity is equal to 1. Now, one more very interesting interpretation from rank and nullity is that whenever you add the rank and nullity of a given graph, you get the number of edges in it. Okay. So let's see in the first figure, if you are adding the rank and nullity R and mu, what we are getting? We are getting 3, and 3 is what? The number of edges in the graph. So likewise, we can see in the next two figures, a graph over 4 nodes and a graph over 5 nodes. So these are all strongly connected components. They have direct connectivity between any node, any pair of node given to us, and we can apply the rank and nullity formulas to calculate further expressions. Now, the weighted graph. Normally when we are talking about the graphs, so what the link that mean is there is a connection, there is a link, there is a existence of communication, or there is a existence of some kind of linkage between two stations. Okay. But when we are adding weight to those link, it means that which of the communication paths, if we are talking in context of networking, say for example, which of the edges are given more importance, maybe importance on the basis of reliability, that is, this link is more reliable than the other links in the network. So it is good for networking purpose, good for communication of messages, etc. Or it can be, say, for transportation network. What happens? Their places becomes the nodes and the roads becomes the links. Okay, and then you get a graph. Now, if I have to travel from a particular distance, say from one node to another, maybe distances apart, those nodes are. So what happens? I will try to take the best route that is possible. Now, the best route possible may be in terms of several parameters, less time to reach, or I want to go to my destination by crossing certain other places in the network. Maybe I'm going from node A to node Z, and I want to travel via some third or fourth node in the path. So I would like to take I would like to customize my path in that manner. And while customization, what is important is which roads are more reliable, they are less congested, or etc. like that. So this can be modeled with the use of weights. Okay. So significance of weights, if we are talking about, and what it could be, let's see. It can be the frequency of transmission of packets during communication cycle. Yes, that's very true. if the transmission of packets on a particular path is more, it means that particular link has been used over time again and again, and there must be some reliability, underlying reliability in that link. So it increases the weight of that, weightage of that link increases in terms of reliability. The second could be the number of messages exchange required. Maybe some protocol is triggered, some communication or routing protocol is triggered, and that particular process may be taking some amount of messages to get exchanged, some control messages, etc. So if some particular link is followed, then how much messages, packets has to be transferred. Again, obviously, the link history, the heuristics we need to concern about, that whether the link in the past has some vulnerability constraint or not, likewise. Or even if we are taking the nodes as states of communication, then it can be some way, like if my communication protocol is in one state and it's jumping to the next state, that is, there is a state transition, then how many messages on average can be required. Okay, so this can be one aspect. Other can be perception of intensity of related object. Yes, then cost incurred in communication in form of maybe distance as a metric, or time delay can be latency, or as we were earlier speaking about the congestion part, it can be congestion. The road with more congestion can be given a higher weight or a lower weight according to the network assumptions. Then a number of parallel lanes that are available between two connected places. Yes, if there are more alternative paths, then the value of that link will get increased. So these are some of the interpretations of what is the significance of the weights when added to the edges. Okay. Now, how these things are stored in form of a matrix, because graph details are generally stored on a matrix. It can be vertices, cross vertices matrix, or vertices cross links metric, etc. So in the diagram you can see that one way is to represent the graph properties is the adjacency list representation. So in adjacency list representation, what happens that we have on the column part and the row part all the nodes, and if any two nodes are connected, it's marked by 1. Okay, we know this very well. And if it's not connected, it will become 0. But in case of weighted graph, what happens? These values changes. As you can see that previously they were all 1s and 0s binary form. Now we are adding the weights. So these are the adjacency list representation of a weighted graph. If two nodes are connected, instead of writing 1, what we will do, we'll write the weight instead. Okay, so this will give more interpretations of how a graph given a network of nodes are going to behave. And yes, weighted graphs are also known as tie strength graphs. So what is the tie strength of each link, how strongly that particular pair of nodes are tied up together. So it's also known as tie strength. Okay, so let's move ahead. Now complement graph. Complement graph is what? It's associated with the property of original graph, say GVE, as the first figure is showing, and the complement graph will be defined as G dash with a different set of edges. Obviously, vertices will remain the same, as V bar and E bar are its vertex and edges set. Then V bar will be exactly equal to V, that is the original vertex set of the graph, of the original graph. And what about the edges set? Now the new edges, the complement graph will have those edges that are not there in the original graph. All the possibilities, all the possible edges that were not present in the original graph, they will come in the complement graph. As in the figure you can see that in the second figure it has all the edges, all the vertices, but the edges are what they are in complement to the original graph G. this is G dash, and it's again subject to the very important constraints that we have studied earlier in case of simple graph, that there is a vertex set. All the vertices should belong to the original vertex set, and obviously there will be no self loops, so I is not equal to j, and no multi links, because not so far we are not dealing with any multiple links, that is multigraphs. Multigraphs and hypergraphs will come later in the discussion. So all the edges are very distinct, so the property that it's distinct, so EI and EK in the section should be null. Okay. And what, since we are also not dealing with the hypergraphs, so our edge sets, they will be connecting exactly to vertex. Okay. So these were the common properties that were there with the simple graph, and when we are generating say complement of that graph, those properties will intact, they will remain intact. Okay. Now what is the significance of generating complement graph? One way of explaining is that they can be very helpful to find out the alternative routes in a network communication or in a transport graph. If the primary route is failing for some reason or other. So, or even we are concerning some AI based applications for finding out say optimized timetable of say some school or college level. There can be even better substitutes. So, whenever we have some particular slots for the students to come to their class and study, there can be other slots as well in which their teachers are free to teach, or the classroom resources are freely available. So obviously in such AI based applications also, if we are interested to find out better substitutes, we can use the complement graph. Now the bipartite graph. Bipartite graph is, it looks something like as in this figure, the first figure. There are two sets of vertices, okay, and from each set to another set, there has to be a link in such a manner that one endpoint of it should lie in the first set and the second endpoint in the second set. None of the vertices in a particular set will be connected with each other. This is a very important property of bipartites, and you can see there in its definition that V can be partitioned into two vertex sets. So now we don't have only one vertex set V, so we have partitioned into V1 and V2. So as you can see that the partitions and edges, they comply with this property that exactly one endpoint should lie in one of the two vertex set, and none of the vertices should get connected if they lie in the same vertex set. Okay. Now the second thing is a complete bipartite graph. As we have a complete graph, when we are concerning about a bipartite graph, there is also a completeness in that. So it's a very special graph. So it's denoted by KMN. Okay. So here what happens, M is the number of vertices in the first vertex always, and the second parameter N will be the number of vertices in the second vertex. Okay. And if there is a connectivity from each vertex belonging to one set to each other vertices in the other set, then it's known as a complete bipartite. That is, all the possible vertices, the paths, or whatever the options you say, they are all connected. So in terms of connectivity, if we are discussing, so complete bipartite is a very ideal definition in context of bipartite graphs. Okay. For example, as we had strongly connected components were one, that there has to be one path. Strongly connected components will be that any two pair is connected. So here also complete bipartite is that any two vertices are connected through a direct hop connectivity. Okay. And in the second figure, you can see that this is a non-bipartite graph. If you just want to clear your doubts, you can see that here B, C, those two vertices, they are lying on the same set and they have got connected. So it violates with the third property of bipartite definition. So this graph will not come under bipartite case. Okay. Now, trees and properties. We spoke about spanning trees earlier also. So we have a conception of what trees in general are. Even in the first lecture also, we started with cyclic properties of graphs. So in this lecture, we'll just focus on the very important ones. What happens in trees, there is only one distinct path available if we are traveling from one vertex to another. Okay, so the tree might have, say, n number of edges, n number of vertices, and corresponding n minus 1 number of edges. Okay, so in the graph, in the figure, you can see that this is a tree. It's a rooted tree rather, because we have a properly defined root. And say if there is a node A in the rooted tree, then we can say that A is the parent to two children. On the right side we have one and the left side. So there is a right child and a left child of node A. But if we are concerned about the root, what we say, we don't call it a right child or a left child, we rather call it a right subtree and a left subtree. Okay. Now, binary tree specifically has some properties. It says that a tree which has exactly one vertex of degree 2, one vertex of degree 2, that is what the root, and each remaining vertex is either of degree 1 or degree 3. So let's see whether this graph confirms to that property or not. Yes, we can see that there is exactly one vertex of degree 2 and each other is of degree 1 or 3, because root is the node that is having degree 2 and node A is having degree 3, and other nodes, they are better known as leaf nodes, so their degree is 1. Now, there is a very important theorem associated with trees, is that number of vertices n in binary tree is always odd. Number of vertex, if you count it, it's always odd. In this figure also, how many number of vertex you can see is 5, n is equal to 5. Now, why this happens? The reason behind is that one vertex, that is the root, is always of even degree and the others are odd. So whenever you add the even part to odd, you get an odd number. That is the reason behind. Okay. And the next theorem is with p number of pendant vertices. Pendant vertices means the vertices having degree 1. Okay. So if you are having p number of pendant vertices in a binary tree, then what happens? The number of vertices of degree 3 is given by this formula, n minus p minus 1. So you can see the calculations over here. The total edges, we know that in a tree, the total edges is obviously always n minus 1. And if we are equating n minus 1 with the number of pendant vertices, p multiplied by 1, because the value is 1, right? And then how many number of vertices are there of degree 3? It's n minus p minus 1, so just multiply 3, that's the value multiplied by the amount, okay? And obviously 2. So if we just sum up all this and equate the equation, then what happens? You find that there is a very nice looking relation between the number of pendant vertices and the number of actual vertices, all the vertices that we have is equal to n plus 1 by 2. So this is an important conclusion over here. Then again, there are some more properties on trees that we will visit shortly. Thank you. Welcome back, viewers. We were discussing about the properties of trees. So just to continue, now let's find out the maximum number of nodes that are there on a particular level. So first we have to know what is the level of a binary tree. So in the diagram you can see that we have here constructed a full binary tree, complete one. Now here the root is concerned with the first, ground level, we can say the first level is level 1. So level 0 or ground level is always reserved for the root node. Okay. In level 1 we have 2 more nodes that are concerned to the left and right subtree of the root, and in this way we have till level 2. Okay. So these are known as the levels of the tree, and the value of the maximum level becomes its height. Okay. So height, if we represent it as h, it will be L max. L is what? The level. Max, L max means here L max is 2. So height will become 2. Okay. So now when we are calculating the maximum number of nodes, how to do it? Since we know that at each level the number of nodes are getting incremented with a power of 2. Okay. So at the first level, at the ground level rather, it is 2 to the power 0, that is 1, that is reserved for the root. Then 2 to the power 1, that is 2. In the level 1 we can see there are 2 nodes. So likewise. Okay. So if we are ideally constructing this, we'll come out with a formula 2 to the power n, which is generally greater than or equal to the actual number of nodes present in the tree. It can be a half tree or full tree, right? It can be a complete tree, non-complete tree. So it depends. So this is an ideal tree. So we have all the nodes over here. So let's check out one more thing here, that the maximum level, if you want to find out the height of the tree with in terms of the levels, then the number of nodes that we can manually count here is 7. Now, if we are trying to compute minimum height on the basis of the levels, obviously it is log 2 n plus 1 overall minus 1. Okay. So if in this particular example n is 7, we just put the value n is equal to 7. What we get, n 7 plus 1, 8, log of 8 to the base 2, obviously it's what, 3, 3 minus 1 is what, 2. So here the minimum height given this many number of nodes, as in our case it is 7, given this many number of nodes, what could be the minimum height of the tree? Okay. So don't get confused with the L max and minimum height, because height can, given the different arrangement of the tree, the height can vary from a minimum to maximum, that we will see shortly. So whatever be the minimum or the maximum case, the level has to be maximum. Whatever the value of the level is, the maximum value of the level is, it will be the height of the tree. Okay. So in this case the L max, value of L max is 2, so the height is 2. But given this arrangement, the minimum criteria will apply. What is the maximum criteria? This is the maximum criteria in the second figure. Here we have a skewed tree, that is skewed towards a particular direction. Okay. So here same number of nodes, we can see n is equal to 7. Now you put it in the maximum height equation, it will give you 7 minus 1, that is 6 by 2, 3. Yes, we are getting 3 levels, 0, 1, 2, 3. 0 again reserved for root, and then what we have done, we have just moved a particular subtree of the given original tree to the right side of the graph, of the tree graph. And what we have found, the constructed the arrangement is known as a skewed arrangement. Okay. So when we are taking a ideally skewed arrangement, we will get the maximum possible height of a tree on this particular arrangement. Okay. So this was about the tree and its properties, as the height, maximum, minimum heights are concerned. Okay. Now the spanning tree, which is much more realistic case, because in most of the applications, rather than applying trees or general trees or say binary trees directly to the case, we apply spanning trees. So we know that what the spanning trees are. Last lecture only we have studied on. Just to recall some important parameters, that we know what a subgraph is, and spanning tree is what? It is a connected acyclic subgraph. The three important keywords just to recall. Connected, it should be connected means that there has to be a path. Acyclic, any edge adding to that graph will result in a cycle. So, we do not want a cycle when we are speaking of a tree. So, acyclic, and yes, of course, it is a subgraph of some given original graph. Here, if in the figure 1, it is a original graph and figure 2 is showing a subgraph. Figure 3 is the spanning subgraph or spanning tree. Okay. So, what it does, it includes all the vertices, make sure that all the vertices are included and no cycles are there, and edges are chosen in a manner that connectivity parameter is not violated. Okay. So, with this concept, we want to know more about minimum spanning tree, because spanning tree is just a concept. When we apply spanning tree to a real life or a real world model, what we do, we tend to find out the minimum of the number of spanning trees that are generated. Okay. This is, you should believe that given a particular graph, you can generate so many connected acyclic subgraphs. It means that there can be more than one spanning tree possibility out of a given original graph, right. So, minimum spanning tree is going to give you that particular edge connectivity, that particular acyclic subgraph, in which if we sum up the weights associated with the edges, it comes out to be minimum. So, certainly it is associated with the weighted graphs. We have seen the weighted graphs, what they are, and it will obviously it will connect all the vertices because it is a spanning tree. Okay. The very important part is it covers minimum weight set of edges. Okay. The weight, the sum of weights that the edges are carrying, it should, when you sum up those edges, it should be minimum throughout, and it is a acyclic graph. Okay. So, given an original graph, there are two possibilities of spanning tree. Okay. The second one is a minimum spanning tree, but the third is also a spanning tree, but it is not a minimum. How? Just sum up the edges, the weights associated with the edges. You can see that in the third figure, the sum comes out to be 14 sum units, and in the second graph it is coming out to be 12. There cannot be any other possibilities that exist which is less than 12. You can just try it out. Okay. So, that is why we regard the figure, the second figure, that is the subgraph that is coming out from the original graph in the figure 1. This figure shows the minimum spanning tree, or in short it is also known as MST. Now, there are different ways to construct the minimum spanning tree given a simple graph, a connected one. So, what are those methods are? If we just take the very simple one, it is a brute force method. The brute force method is what? You are taking into consideration all types of possibilities that are there. Okay. So, you are checking out every edges, and you are checking out with every weights associated with it, and then you are summing up after the spanning tree is created. So, this becomes actually a very tedious task, as the number of nodes tends to increase, because this total number of possibilities, 2 nodes taken at a time, it results to n to the power n minus 2. Here in this case, though the number of nodes is how many? We have 6 nodes, right. So, it is 6 to the power 4, it itself is a big value, but the transportation graphs are so big, most of the real graphs, not only transportation taken as domain, but any real world graph, they are so huge, and believe me, there are like thousands or even more than thousands of nodes are there. So, this is practically not feasible to calculate, just go on calculating the weights and constructing the spanning trees, minimum spanning trees, and okay. So, this is a very tedious task, and it is even not practical also when we are trying to compute it on computer itself. So, what we do, we take up some greedy techniques. Okay. So, two very important ones are Kruskal's method and Prim's method. So, let us take Kruskal methods first. Now, Kruskal method says what? that arrange all the edges in ascending order of the cost or the weight. There is a weight can be cost or it can be delay, as we have discussed about what different interpretations weight can have. Okay. So, what we do, first we arrange it in this order that we have already done arrangement, and then what, we keep on adding the nodes, or we keep on just darkening the edges that in the order as it comes. Say for example 3, 5, figure 1 shows the original graph, right? From figure 2, the first edge that we have here is 3, 5, the edge between the third node and the fifth node, and it is the least one, it is having the weight that is the least among all, okay, 18. So, we have just darkened it. Likewise 1, 7 is the next, so we have darkened 1, 7. But be careful that while constructing this spanning tree graph, we have to keep in mind all the constraints that spanning tree is having. It should not turn into a cycle. Okay. So, when we have 3, 5 and when we are adding 1, 7 into it, we have to check it out that whether a cycle is being formed or not. So, no cycle, then it is okay, fine. We move ahead, then we have 6, 7, okay, constructed. Likewise 0, 2, that is also fine. So, likewise when we go to 0, 1, what happens in figure 7? 0, 1 will result in a cycle, right? How? 0, 1, 7, they are all in a triad. So, it will violate the concept of a tree itself, right? So, we discard that, we have put a cross mark. The next in the possibility is 3, 4, then check it out whether 3, 4 adding this edge will create a cyclic, it will violate the cyclic property or not. So, it is okay, fine. And similarly we go on, and before adding 4, 5, we can see that again a triad is being constructed. 3, 4, 5 will become a triad. So, we discard it and 4, 7 is taken rather in its place, and finally you can see that in the 8th figure we have constructed the MST. So, no need for n to the power n minus possibilities, no need for exploring so huge number of possibilities. We have in simple 8 steps, not even 8 steps, we have started from 1. So, we can say that in 7 steps we have constructed the minimum spanning tree. Okay. So, this was Kruskal's method. One more method is there, that is Prim's method. Okay. Now, what Prim suggested is, let us begin with a particular vertex, say 0 or any other vertex you can take up, okay, and then greedily expand the tree, keeping in mind the properties should not get violated, properties of a simple spanning tree. Okay. And what? At the cheapest age, that exactly one endpoint it's there in the growing MST. Okay. So, let us see how. In the first example, what are the different possibilities? If we are starting from node 0, there are 0 to 2, 0 to 6, 0 to 7, these are all connectivities associated with the node 0. Okay. So, which is to be taken? It is 0 to 2, because 0 to 2 among all the 5 possibilities, 0 to edge is giving you the minimum value. So, we choose 0 2. Once 0 2 is fixed, it is darkened, okay, leave it. Then what else possibility we have? The others, okay, 0 2, leave out 0 2, then we have 0 7, 0 1, 0 6 and 0 5. Among those, 0 7 is the next minimum, so 0 7 is used. And now when we have arrived on node 7, we have 3 more possibilities, that is 1 7, 6 7 or 7 4. So, what we can see over here, that at each stage as we go on spanning the vertices, more possibilities are just coming up, and we are choosing the minimum edge from those selected possibilities. Okay. So, it becomes rather easier. So, this way it goes on, and finally in the last figure you can see that our minimum weight spanning tree has got constructed. Again, we don't require to just go on searching for so many possibilities. We just are, what we are doing, we are starting from a particular vertex and greedily growing the tree in a manner that its properties get intact, and there's so vast number of possibilities to be searched on, that tedious task is also alleviated. Okay. Now let's talk about the graph metrics. Okay. Metrics are very important to find whether a graph is efficient in a particular manner or not, given some domain or some application context, etc. Okay. So let's see. The first one is clustering coefficient. Okay. As we were just seeing, that clustering coefficient is nothing, the very simplest way of defining a cluster is the triads. Triads means that the triads or triplets, that is 3 nodes connected to each other, is called a triplet. Okay. So how many number of triplets are there in a graph will certainly help you out to find out whether there is there are some chances to get a strong cluster, strongly connected nodes, and they're strongly connected with each other, strongly connected subset, etc. So this is what the clustering coefficient will simple out your efforts. Okay. So let's understand what a clustering process is. Clustering is what? It is merely processing the groups that are closely connected to each other. Now this close connection can be in terms of some spatial properties, that they are closely lying, some places that are easy to reach, so in a given proximity. So they can become, they can form a particular cluster. So depending upon the spatial distribution, the cluster can be formed. Else it can be say some temporal functions, that for a particular time some workstations have to turn up. Say for example, we have a network of workstations, 10 workstations. Okay. So using 10 workstations for communication purpose, communication of say wireless communication that we are talking about. So what the administration might have scheduled is that 5 out of 10 transmitters will switch on for say 12 hours, and for next 12 hours the rest 5 workstations will turn up. Okay. So since on the basis of time the functions have got defined, so we can say that on the basis of temporal functionalities also, if we want, we can do a clustering. Mostly on the basis of spatial, that is with respect to space, those who are connected closely, etc. Those clusters are done in that manner. Okay. And clustering of an undirected graph is always measured by this parameter clustering coefficient, that is given by equation, as you can see, Ci, that is the clustering coefficient of the ith node. It is found out as 2 of Ni. Ni is the size of the neighborhood of the node I, and it's a ratio to delta I and product of delta I minus 1. Delta is what it signifies the degree of that particular node. Now we can go on calculating the clustering coefficient of each node, as it says that it's a measure of average probability of any 2 neighbors of vertices in the close neighborhood of that particular node. And if we are going just calculating all these values, and we can find out, we can keep a threshold actually, and if we can see that if a node is going beyond this threshold, then there is a chance that this node can be a part of even bigger cluster. Okay. So clustering coefficient gives you an insight whether there is a chance of clustering even more into even more bigger clusters or not. So this can be found out. Say we have some threshold alpha. So if Ci is greater than equal to alpha, we can form a cluster with a nearby node. Now comes the graph density. We have a graph, say for example the first example that is given, and we can check out that what are the total possibilities that we have when we are constructing a graph with same number of nodes. Certainly these are not the complete edges that we have. in a graph, if it is a complete, that is each edge is strongly connected to each node is strongly connected to each other nodes in the network, that is when we are talking about a strongly connected graph, then what happens? The number of edges are obviously, it will tend to increase, right? So when we are comparing a particular given graph to that strongly connected version of itself, we can find out to what extent the given graph is dense. As for the first one, it says that it is 25%, it's merely 25% of the actual possibilities that can have with the same number of nodes. So the number of edges that we have with the first figure, it's not strongly connected, so we have lesser number of nodes and they are less by 20, it is just 25% of the actual possibility. Okay. Similarly, if the next graph, you can see the next graph here, the density is higher, but it's not completely connected, it's not strongly connected. So still we have like it's only 39% towards 100%. So likewise, what we can do, we can just go on calculating it, that E here you can see that it is a number of edges that are actually there in the graph. Okay. And E is divided by the whole possibilities that are there, that is n multiplied by n minus 1 by 2. There is a maximum possibility of edges that a graph can graph with some number of nodes can have. Okay, just it's a ratio. It's a ratio that helps us to find out that out of the maximum sample set what we have, and then find out the ratio. It will help you to check out the density, that by what factor the density can be increased or decreased likewise. Okay. Then of course we have geodesic. Geodesic is a term that is basically referred to as shortest path. Okay, shortest path between any two nodes in G. Instead of calling it a shortest path, we often call it a geodesic. Okay. Now geodesic is represented by small g, and when we have a term like g to the power k of the graph capital G, then what it signifies? It signifies the total number of geodesics that are there of length k. To the power k means of length k between a given pair of nodes. Okay. So let's see here. Here G is what? It's just a adjacency list representation, nothing else of the given graph here. So it simple G, if we are checking out the entries of simple G, then it only says the number of geodesics, that is the number of shortest paths that are there between any node I and j of length 1, because G is synonymous to G raised to the power 1. Okay. So now when we are squaring the matrix, squaring by itself, G square, it means that now it's showing the number of shortest paths or number of geodesics that are available of length 2 between any pair of nodes. Okay. Let's see one example. In G square matrix, you can see that 4 cross 4th element, what it says that there are 3 geodesics, 3 number of geodesics, okay, from node 4 to 4 of length 2. That is, we are on node 4, and if you want to reach itself only, then how many ways are there? There are 3 ways, and all these 3 ways are of length 2. Let's see how. If you are in at node 4, you can go to node 2 and then come back to node 4. So that is how many paths? 2 paths. And how many such possibilities? 3, via 2, via 1 and via 3. Okay. Let's check out one more. In the last row, third column, we have 0 over here. It means what? It means that there are no geodesics from node 4 to 3. 4 means if we are positioned on the node 4 and we are going to node 3, then there are no geodesics, no shortest path of length 2. Okay. Because we can see that it's directly connected, so there is only one path, so there is only one geodesic possible from node 4 to 3 of length exactly 1. So in the adjacency matrix, in the above adjacency matrix of G, you can see that at that particular place where we have 0 in G square matrix, we can see that there is a 1 over there. Okay, that is the interpretation. Now, a theorem is there in this context which says that for some positive value of k, if all the elements of matrices GK is found to be non-zero for some value k, any positive value, then we can say that the graph is connected. Okay, just go on multiplying the matrix with itself, and at some point of time, if we come to a conclusion that none of the elements, we can see that in G square there is a 0, it's there. So if we just continue going, squaring it, and then g to the power 3, 4, like that, and at some point of time if we find that all the elements are non-zero, it interprets that the graph is connected. Okay, so this basically helps in finding the centrality issues, or keeping track of diffusion process. Diffusion process means what is the rate, what is the pattern of spread of information in a given graph, etc. Okay. Now, the diameter and the average path length. The diameter of a graph is very important. It often helps you to answer certain questions, like let's frame the questions. What is the expected distance of maximum separation? Okay, this can be one way. Other can be how long on average is required to move on any node to any other node in the network, or say at what estimated rate would tend to spread the information, at what rate the information would likely to get spread in the network. Okay, if we are concerned about the first question, it can be answered by diameter. Okay, see, diameter is what? It is nothing but it's related to geodesic only. It's the largest possible geodesic. That is, geodesic is what? It's the shortest path. So the largest possible shortest path. So it's a little, the term is might be a little difficult to follow, because we are in the same line we are saying the largest shortest path. Okay, so it's better to signify as largest geodesic. If it is a connected graph, then it will be certainly the largest component, the geodesic of the largest component, and it is basically what? The smallest possible distance between a pair of nodes that are distant apart. Distant apart means maybe those two nodes, any two nodes that are at the two extremes of the network, then what is the distance, and call it a shortest distance. What is the shortest possible way to reach from one node to another, specifically when those two nodes in context, they are distances apart. No more pair of nodes are such distances apart, say. Okay. Second question can be answered by average path length. Average path length would be simply the average geodesic. And the third question can be answered by diffusion. Okay, it will come later in the discussion. So let's see what diameter and APL is. Say we have taken a very simple form of graph, a ring structure. So a ring looks like this, as in the figure. A ring can be spanning over even number of nodes, or it can be spanning over odd number of nodes. Here in the figure we have taken even number of nodes. We can say that this is an even ring. Okay. So when we have an even ring, the diameter is n by 2. Okay. Otherwise it is n minus 1 by 2. So what happens in this ring structure? Say we have marked 2 points A and B, and A and B are those two nodes that are maximum distance apart. Okay. So what is the distance? What distance means? The number of hops we are talking about. How many number of hops has to be traversed if we are trying to move from A to B? So it is nothing, just put the formula and you find 3. So let's check out whether it's really 3 or not. You can see that from A to the first dot, the second dot, and then B. So it's yes, it's 3 hops. Next, if we take a binary tree. Binary tree, we know that there are L levels and, or we can say L depths. So here we apply a simple formula, n equal to 2 to the power L plus 1 minus 1, that is the at a particular level how many nodes are possible. So just do a little calculation and we find out that for a particular level L, or the maximum possible nodes are there, or in the otherwise if there is these many number of nodes, then till how many levels we can cross. So the thing is, the main idea is to find out the value of L, the value of the maximum value of L given a number of nodes n. Okay. So once we have the value of L, diameter will be what? You can see in the figure that here the diameter is for the two distant apart nodes, that is A and B, in a particular left subtree, and one is on the particular of right subtree. So here we have to cross all the three levels, and right, 2 levels we are crossing, given level 1, or we can synonymously call it a level 0 or ground level where the root is stationed. And this diameter of binary tree would be nothing but twice of the L. Okay. So 2L will give you an expression, and we can see that this is nothing but it's of order log 2 n plus 1. For large n, plus 1 will just vanish out. So we get this value for diameter of binary tree, and this is all from this lecture. Thank you.
Friends, on that note, I would like to thank ma'am for this very enriching discussion, and thank you dear friends for watching our show. Stay tuned and keep watching. Thank you.